Okay, the idea of this example is to demonstrate how we can use conservation of linear momentum, or Newton's second law, to calculate the forces required to keep a pipe fitting in place. So we're considering what's known as a reducing elbow. Flow is envisioned to enter from the left, pass over section 1, before being redirected through 90 degrees, and expelled through a smaller opening at section 2. Now, because the direction of the water's flow is changing and the speed of the water is being increased because of the smaller outlet area at section 2, we can infer that there's a change in the momentum of the fluid as it passes from section 1 to section 2. So in order for that momentum change to occur, there has to be a force acting on the fluid system. That force comes from the pipe walls, and thus some anchoring force has to be supplied to the pipe fitting to keep that reaction force from sending the pipe flying off into space. So we might imagine, for example, that these flanges at section 1 have some through-bolted connections. And it's our job to find out what the horizontal and vertical reaction force at these flange bolts, or the reaction or the resultant force of these flange bolts, is if the pipe is to stay in static equilibrium. So our first step in solving one of these control volume problems is the selection of a control volume. So we're lucky in that we're told at the problem outset where inflow and outflow from the pipe is occurring. That is, we know that inflow is limited to section 1 here. Let me change colors. Is limited to section 1 here, and outflow is limited to section 2. In other words, there is nothing, no fluid is leaving or entering our pipe through any surfaces but control surfaces 1 and 2. So our choice of the control surfaces between 1 and 2 is rather arbitrary. They can be any shape we like, and because there's no flow being carried across those control surfaces, they'll simply fall out in the math. So for simplicity's sake, let's presume that our control surfaces constitute a rectangular surface that cut through sections 1 and 2. So our control volume can be drawn as such. In a black box sort of form, we have a box here, which is our control volume, bounded by control surfaces, and we know that we have inflow at section 1, and we know we have outflow at section 2. So these are the two control surfaces in which we'll actually be interested, because as I said, there's no inflow or outflow occurring through any of these other control surfaces. So momentum, mass, any of our intensive properties cannot be carried across those surfaces at all. So let's round up what we know about these control surfaces next. For control surface 1, we are not given the velocity yet. We are given that the area of 1 is equal to 0.01 square meters, and that the pressure of 1 is equal to 220 kilopascals, and this is measured in absolute pressure. Right? This means it's with respect to a perfect vacuum. At control surface 2, we are given that V2 is equal to negative 16 J meters per second. We've inferred, right, the direction here. We're really actually only told that V2 is equal to 16 meters per second, but we can see by inspection that it's expelled from the control volume downward. We're given that A2 is equal to 0.025 square meters, or rather, sorry, 0.0025 square meters, and P2 is equal to P atmospheric, or 101 kilopascals absolute. The next step is to tally up all of the forces that are acting on our control volume and control surfaces. So this will take the form of a sort of free body diagram. So free body diagram of control volume and control surfaces. Now, the forces that we might expect to see acting on our control volume here and control surfaces come in a couple of flavors. For example, we've heard about body forces, right? These are forces that occur acting on the actual mass of a fluid, things like gravitational weight, etc. The idea here is that body forces act inside of our control volume, right, where the fluid is actually contained. And in this case, the only one that we're going to account for, right, is gravitational weight. So we have the weight of the fluid, and we have the weight of our pipe elbow. And we're not actually going to calculate these explicitly. So let's just sum the two of these things up together by a force W. So, if I may draw my imaginary control volume here, let's go ahead and establish an XY coordinate system. Then somewhere inside of this control volume will be a weight, right? If we have our pipe elbow in here, and then besides body forces, right, we also have what we call surface forces. And surface forces, the ones for which we can solve, act at the control surfaces. And these include water pressure distributed over sections 1 and 2. The reaction forces, or anchoring forces that keep that are somehow being exerted on this section of pipe to keep it anchored in place, and atmospheric pressure acting over the remainder of our control surface. So let's draw the first of these items, right? The water pressure distributed over 1 and 2. What this means is we have right, acting at section 1 here, we're going to have some uniformly distributed pressure with a force that's equal to P1 times A1, right? At 2, we're going to have another uniformly distributed pressure, which is equal to P2 times A2. Our reaction forces, right, we've imagined that we have some sort of anchoring connection over here at the inlet to the pipe that keeps everything in a static equilibrium. We'll go ahead and draw those as Rx and Ry. A quick note here, we don't yet know the directions of our x and our y. So just as we would in statics, we're going to draw them with a positive sign convention with respect to our x and y coordinates here. And in the math that we'll be stepping through as we solve this problem, the signs of the computed values of our x and our y will tell us whether they are actually directed along the positive or negative respective coordinate directions. And then the last of these surface forces comes from, as we said, atmospheric pressure. And this is something I want to spend a moment discussing. Right? So every part of our control surface that is exposed to the atmosphere is going to have a uniform pressure acting on it. Let's finish drawing those. So I want to take a moment to discuss the way that we treat pressures. Right. So far, we're working in absolute pressures. Pressures measured relative to absolute vacuum, or pressure of 0. But what I'm going to show here is that we have a much easier time. It simplifies our calculations significantly if we work in gauge pressures rather than absolute pressures. So if we were to calculate the net force of pressures, right, acting on anything, in this case acting on our control surfaces shown here, we would write this just as we did in the hydrostatics work as the integral over the control surface of negative p times the normal vector along dA. Remember that this negative sign, we include this negative sign because the pressure is directed inward, whereas the normal vector is directed outward. So this accounts for the fact that the normal vector on the surface and the pressure point in different directions. So in this case, this would can be written, right, if this is, this is negative P absolute pressure, right, times NdA, which could also be written, if we wanted to substitute for absolute pressure, we could say this is equal to negative P gauge pressure plus P atmospheric, right? So, distributing our normal vector in dA into the parentheses here, we can split this into two integrals, where this turns into negative integral over the control surface of P gauge dot N dA minus integral over the control surface of P atmospheric N dA. Okay, what's the significance here? Well, if we make the assumption, right, that the atmospheric pressure is constant, around our control surfaces, this is usually a good assumption if our object that we're considering is small. Okay, because there isn't very much fluid static pressure variation between the top of this box and the bottom of this box, and so the integral of a constant pressure around this surface, right, because we have this normal vector here, and if we're integrating around a closed surface, this quantity on the right is going to go to 0, which means that we're left with the same pressure force calculated using gauge pressures rather than absolute pressures. So what we've done is we've subtracted out a constant pressure from all of the pressure terms, taking them all from absolute pressures to gauge pressures. So in other words, let me copy this briefly. In other words, our full distribution of surface pressures, right? Let's get rid of everything that isn't pressure. Right, this quantity, or this schematic here, is equivalent to P1 minus P atmospheric, which can be thought of as P1 gauge, right? If this is P1 plus that uniformly distributed atmospheric pressure that occurs everywhere, distributed all along the outside of our control volume. So I won't draw all the arrows here, but the idea is that the integral of pressures around this this sketch on the right-hand side, this goes to 0 because all these atmospheric pressures cancel one another out. So this is a roundabout way of saying we can simplify the forces that we have to account for by recognizing that atmospheric pressure is going to cancel itself out, and so the pressure force at the outlet area 2, right, because it's exhausting to the atmosphere and is a free jet and thus has atmospheric pressure, that gets subtracted away as well. So the only pressure force, the only surface force due to pressure acting on the control surfaces is created by this high pressure region at the inlet area 1. So let's wrap up what I'm saying here with sort of a finalized free body diagram that we'll use for reference. So our final free body diagram we'll have force, we'll call this force 1, which is equal to P1 gauge times A1. There will be a weight and Rx and Ry. So writing out our sum of moments, we can come up with sum of forces, or sum of the forces rather. The sum of the forces in X. This is equal to Rx plus F1 and is equal to the rate of change of X momentum contained within, or of the system contained within our control volume. And then sum of the forces in Y is equal to Ry minus the weight equal to the time rate of change of mv, that is the vertical momentum component of the system contained within the control volume. Okay, so step 3 in our solution calls for us to formalize our governing equations. The first of our governing equations is going to be conservation of mass, or the continuity equation. Right? And this one's familiar as stating that the time rate of change of the mass in a system is equal to 0, or that 0 equals let's write it in its most simplistic form first, right? What this states is that 0 is equal to the time rate of change of mass in a control volume minus the flow of mass into the system through control surfaces plus flow rate of mass out of the out through the control surfaces. Written more generally, this appears as partial time rate of change of the control volume rho dv plus the integral over all of our control surfaces of rho v dot n dA. Our second governing equation here is going to be conservation of linear momentum, right? And this is what we've already started writing up in this box above. But what it says is that some of the forces, right, on of external forces acting on the control volume and control surfaces is equal to time rate of change, control volume's contents of rho v plus the integral over our control surfaces of rho v the flux of rho v across of our control surfaces. Okay, so another, we can step in at this point and recognize one sort of simplification here, right? We've already established that flow into the system only occurs, right? If this is our control volume, that flow into the system only occurs through section 1 and only occurs out through section 2. All right. In other words, because the flow is either because there's no flow across any of these other boundaries, this v dot n term in our integral goes to 0 everywhere except at control surfaces 1 and 2. So in all these red boundaries, they simply disappear from our integral. So we have a well-defined flow in and well-defined flow out. So we can go ahead and break up these governing equations one more step. You say is equal to ddt, the control volume's contents of mass, plus the integral of control surface 1 of rho v dot n dA, plus the integral over control surface 2 of rho v dot n dA. And then for conservation of linear momentum, right, this tells us that sum of the forces is equal to time rate of change in the control volume of rho v dv plus the integral over control surface 1 rho v dot n dA plus the integral over control surface 2 of rho v dot n dA. All right, at this point, let's go ahead and sort of see what we can do to make these equations a little bit simpler. So let's list, right, so for part 4a, let's restate our assumptions, or list the assumptions that we're making in this analysis. One, in the problem statement, it was proposed that the flow is steady. And as a consequence, this means that all of our time derivatives go to 0. So we can get in here and we can say that this first term goes to 0 for conservation of mass, and this term here goes to 0 in conservation of linear momentum. Assumption 2. We're going to assume that we have a uniform flow at 1 and 2. That is, we're assuming that that the flow into 1 doesn't have any kind of weird velocity profile. It's simply equal to v1 all the way across the area 1. And likewise, the flow out from v2 is also uniform. Our third assumption is that this is incompressible, but also that it's a homogeneous, right? That our density is homogeneous. So this means that the density is constant. And so, this first assumption allows us to cancel out the time derivative from our governing equations. But the assumptions numbers 2 and 3 are also very useful because taken together, these allow us to simplify our integrals by moving v and rho outside of the integral. Right? Because these integrations are taking place over space, and we've established that both the velocities and the densities are uniform at the inlet and the outlet, then they no longer vary inside of the integrand, and they can simply be carted outside of the integration symbol, which simplifies things considerably. So recognizing these 3 key assumptions, let's take step 4b and simplify our governing equations. So first we'll start out by removing the time derivative, recognizing steady flow, and then we will implement the second and third assumptions in order to simplify our integrals. One moment. I need to recharge my stylus for a second. Okay. So, as I said, let's begin by eliminating this time derivative to recognize steady flow, which means that for conservation of mass, say mass 0 is equal to the integral over CS1 rho v dot n dA plus the integral over control surface 2 rho v dot n dA. And then for momentum, we have that the sum of forces is equal to integral over control surface 1 rho v dot n dA plus the integral over control surface 2 rho v dot n dA. So as I said, what the second of our 3 assumptions allows us to do is recognize that our v's, right, can be moved essentially outside of the integral. There's one thing we want to do first. These v.n terms will make life a lot easier for us if we figure out what those do inside of the integral. So let me draw, again, another little representation of our control volume. Say, what about v.n? So at control surface 1, right, we know we have velocity in, and at control surface 2, we have velocity out. However, by convention, remember, whenever we have a control volume, the normal vectors always point out from, always point outward from those that control volume and into the fluid. So normal vector 2 looks like this, and normal vector 1 looks like this. So what this means is that at control surface 1, right, the velocity and the normal vector are pointing in opposite directions. At control surface 2, velocity and the normal vector are pointing in the same direction. So what this means is that on control surface 1, v dot n, right, this is going to be equal to negative v1, right, where v1 is going out, and v2 is out. And control surface 2, v dot n is going to be equal to simply positive v2. So this occurs in the momentum equation 2, where v dot n at control surface 1 is going to be uniform v1, and control surface 2 is going to be, negative v1 at positive v2. And so now, if we take the second and third assumptions there, this allows us to carry, right, rho v1 outside of the integral, rho v2 outside the integral, rho v1 outside the integral, rho v2 outside of the integral, which leaves us with essentially rho v1 times v1 a1, right, with a negative sign carried down there, plus rho the vector quantity v2, right? We haven't established yet the direction of v1 and v2 as velocity vectors. If a velocity here is drawn without the over bar and arrow, like in this v1 a1, this simply correlates indicates the magnitude of that velocity. So plus rho v2 a2. Or in other words, right, if we move this over to the left-hand side, this tells us that rho, I apologize, that v1 is not supposed to be there. I'm getting ahead of myself here. That's what happens in the momentum equation. We end up with rho v1 a1 is equal to rho v2 a2, which can simply be thought of as the mass flow rate through the system, or rho times the volumetric flow rate through the system. All right, now let's apply the same approach to the momentum equation. Now we get to carry those vector v's outside of the integral. I apologize for doing that prematurely. But what this tells us is then this is equal to rho v1 a1 minus rho v2 a2. Or if we go ahead and see what we got from our mass equation over here, right, and we make the substitution of v1 a1 or v2 a2 into our expression over on the right hand side, we can get rid of either this v1 a1 or this v2 a2. Now we've been given v2 a2 right off the bat as part of the problem statement, so why don't we just make the decision that we'll substitute v2 a2 into the problem. So this means we end up with rho v2 a2 Okay, so at this point, now we're ready to go ahead and start plugging things in and finally getting around to getting a numerical solution for our to the problem. So what do we know and what don't we know, sort of going into this, all right? Our unknowns include still Rx, Ry, and, right, we still have a V1 over here that we haven't yet determined, and V1 in vector form. The equations that we have that we can utilize to solve for these unknowns include A1 V1 is equal to A2 V2, right? This is a consequence of our conservation of mass, where we recognize that density is constant. We can divide it out from both sides. We have sum of the forces in X is equal to, let's go ahead and provide some extra space here. Sum of the forces in X is equal to rho A2 V2 U2 minus U1, which is equal to Rx plus P1 gauge times A1. And we have sum of the forces in Y is equal to rho A2 V2 V2 minus V1, which is equal to Ry minus weight. Now see what I've done here. I've taken this vector, right? I've taken this vector equation here, and I've split it into two equations, one for the x component and one for the y component. So first, let's go ahead and find V1. So by using our continuity equation right here, we can state that V1 is equal to V2 times A2 over A1. This turns into 16 meters per second, right? So this is the magnitude of V1. This doesn't yet indicate the direction. 16 meters per second times 0.0025 square meters over 0.01 square meters, which leads to answer 4 meters per second. Okay, now in order to figure out the direction of V1, we're not going to do anything more complicated than just looking at the picture of our flow. So if I move back up, right, we can see that V1 is entirely in the positive x direction. Okay, and moreover, we can see that V2 is entirely in the negative y direction. We mentioned this earlier. So let's go ahead and write that V1 is equal to V1 I plus 0 j, or 4 meters per second I plus 0 j. And V2 is equal to 0I minus V2 j, which is equal to 0 meters per second I minus 16 meters per second j. Right, where this is U1, this is V1, this is U2, and this is V2. So at this point, we have everything we need to go ahead and solve for the forces in X and the forces in Y. So next, let's solve for Rx, right, the anchoring reaction force in X. So this tells us that Rx is equal to, plus P1 gauge times A1 is equal to rho A2 V2 U2 minus U1 or Rx is equal to, and we'll start plugging in values here. Rho, we'll assume that this is 1,000 kilograms per meters cubed, times A2, which is 0.0025 meters squared, times 16 meters per second. And U2, right, if we look up here, U2 is equal to 0, and U1 is equal to 4 meters per second. So this turns into negative 4 meters per second. And I've subtracted over the P1 gauge times A1. So this turns into P1 gauge, right? P1 gauge is equal to our 220 kilopascals absolute minus 101 kilopascals, which is the absolute which is atmospheric pressure. So in other words, that leaves us with 119 kilopascals. So minus 119,000 newtons per meter squared times 0.01 square meters, which is A1. And what this leaves us with, right, if we start multiplying everything in here, what we're going to get is 1,000 kilograms per meter cubed times 25 10,000ths of a square meter leaves us with about 0.25, or rather 2.5 square meters times negative 4 meters per second squared, right? Leaves us with 10 and 16, so we end up with approximately 160, negative 160, and let's figure out our units and make sure that we're everything here is copacetic. Kilograms, right, per meter cubed, meters squared, meters per second, and meters per second, which means that cancellation, this cubed, squared, that can disappear, which gives us kilograms meters per second squared, or 160 newtons, and then minus 119,000 newtons per meter squared times 1/100th a meter gives us, or square meter, nets us negative 1.1, or sorry, 1,190 newtons. So the final solution here, right, Rx is equal to negative 1.35 kilonewtons. And finally, our last item to solve for is Ry. So we've established that Ry minus W is equal to rho A2 V2 V2 minus V1. And now let's we're going to perform the same calculation here, but let's sort of do it in a different order so that we get a different appreciation for the way that momentum flux can be envisioned. So if we say Ry is equal to 1,000 kilograms per meter cubed times 0.025 0.025 meters squared times 16 meters per second times, in this case, V2 minus V1, right? V2, we have negative 16 meters per second. V1, we have 0. This turns into negative 16 meters per second. I want to take a moment to just highlight like what form these take. So, right, A2, V2, these two terms, these tell us the volumetric flow rate through the system. Okay, this is the amount of volume per unit time that is passing through, through the control surfaces, and then this, and then when we multiply it by the density of the fluid, right, this tells us the mass flow rate of the system, and then finally, right, velocity. If our extensive property B is equal to, right, momentum, mv, and remember our intensive property, or the amount of momentum per unit mass, is simply defined as v. So in other words, this v2 minus v1, it tells us the deficit in vertical component of momentum per unit mass entering the system. So this gives us right, the change in, say, the change in momentum per unit mass, and then so by multiplying the change in momentum per unit mass by the mass flow rate, what we get is the rate of change of momentum. And so this is a sort of a physical breakdown of how these different terms, interact in order to yield a net reaction force, Ry. So plugging these values in now, right? Once again, we're going to have our 1,000 kilograms per meter cubed, right? Our m dot term here is equal to 1,000 kilograms per meter cubed times, so it's going to be 2.5, 16, 64. This entire quantity is going to give us 640. Oh, I forgot our minus the weight, plus the weight, rather. Moving the weight of the fluid in the pipe over onto the right-hand side is going to give us 640 newtons plus W. Is that correct? Yep. Okay, so if we wanted to break this down into our mass flux terms and our rate of change of momentum, right? What this would turn into is m dot is equal to in this case 40 kilograms per second, and the sort of the specific change in momentum, if you will, mv per unit mass is equal to then the negative 16 meters per second. And so once again, right, our units here work out to be kilograms meters per second squared, giving us the 640 newtons. And so as a last note, right, we're leaving W here undefined. We haven't stated what the weight of the fluid inside of the control volume is, but by leaving it symbolically this way, if we were told, that the pipe has a certain volume, we haven't been given that information. Perhaps the pipe contains a certain volume of water, and perhaps the pipe is made up of some material and has its own weight. If we were given the weight of the fluid in the pipe itself, we would simply add them in here to figure out the reaction force. So what we have here is that the X reaction force is directed to the left, and that the Y reaction force, sorry, this should be a minus sign here. I forgot about the minus on our negative 16. That the Y reaction force is directed downward. All right, so this is telling us that our anchoring forces, on our pipe, are actually pointing in this direction, right? And so let's think about whether that makes sense for a moment. As water, right, enters from the left into the right, that fact that it's being robbed of horizontal momentum, right, of momentum in the X direction by the redirection of the pipe, this is going to fairly intuitively, there's going to be higher, it's going to result in, the water is going to be pushing on the surface of the pipe here in such a way that it's going to be trying to push the pipe away from this junction. Additionally, that's reinforced by the pressure at this junction right here, which is greater than atmospheric. Secondly, as the water is expelled through the bottom of this pipe here, this is going to create a reaction force. Think of letting a balloon go or something, right? The expulsion of momentum from the system. In other words, we've taken a system or a control volume that has no vertical momentum flowing in, and we're throwing a bunch of that mass out the bottom. That change in vertical momentum is going to try to push the pipe up, right? So this pipe is going to have a tendency to want to fly off in this direction. And so our computed reaction forces that keep it in place, right, are going to be directed in the opposite direction from that. So we'll have our X and our Y. And so that was a lengthy but hopefully more clear walkthrough of how we use conservation of linear momentum with a defined control volume to calculate reaction forces using and connecting that with Newton's second law.